在去看影片的时候，你们都会突然想到我在讲什么。因为我们年轻的时候上课的时候，老师上面推东西，我也是推着我的班长推。可是那时候我是在你们，我也知道，就是我脑子里面想的东西，不是我老师讲的这些。
好励志哦！
什么？
老师你好励志哦！
比较励志。那个，你们听得懂吗？就是大致上这门课，是吧？英文上没什么问题吧？这是一门this is supposed to be an EMI course. The entire course is supposed to be like how you get English.
EMI 是哪3个字的
？English medium instruction. Okay. So this is supposed to be to help you guys read and mostly read something, and mostly to listen to things that might be useful, because most of the stuff right now that are useful, the language is English, okay, in terms of content, okay? Textbooks, videos. But I'm thinking, okay, more and more is going to be in Chinese, okay? 在 B 站网站上已经有越来越多这种 useful content， 之前是大部分是英文，现在是越来越多。我估计很快，我不知道多快，in short time, okay? I think probably, okay, so this. I'm not gonna draw this. Anyway, so this is supposed to be in my course, and you guys should try to read the book. Have you guys read the book yet? Have you read the book yet? No? Okay. If you read the book, you'll find that whatever I talk about in class is going to be more understandable to you guys. Okay? So previously, okay, we talked about, we described qualitatively, okay? Qualitative, as you increase the potential to know, okay, you can increase the current, okay? And then if you decrease the potential to know, So previously we talked about the relationship between U, okay? So at equilibrium, okay? The net change in reaction is equal to 0, right? Okay. And so, at equilibrium, okay, the potential is equal to U, okay? So depending on where the potential of the metal is, okay? If it's higher up, then it's gonna be in the another region, okay? If it's lower than that, it's gonna be in the cloud region. Talked about that previously. Okay? So the rate of this reaction, okay? This is a forward reaction, okay? The rate of this, forward reaction, okay? Is a function, okay, of the oxidative species concentration, okay, plus and the Kf, okay, right? The rate of the forward reaction, okay, is a function of the oxidative species, okay, and Kf, right? And this Kf, okay, this Kf, okay, in terms, okay, is a function of numbers, okay? Okay, this is the change in Gibbs free energy, okay? And this delta G, change in Gibbs, this is the Gibbs energy difference, okay, between initial reactant and transition state. Okay, the energy difference between initial reactant and transition state. Okay, what do I mean by that? Okay, so we have a reaction. Okay, like this. Okay, so this delta G right here. Okay, let's say this is the reaction. This is the oxidized state. Okay, this is the oxidized state. And this is the reduced state. Okay. Okay. And then this is energy. Okay. So this is energy. Okay. So delta G. Okay. Delta G forward. Okay. Is this from here to here. Okay. So So, and this is to reduce it, okay? So in order for the reactions to go forward, okay, it has to overcome this energy gap, okay, this energy barrier, okay, which is the activation energy, okay? Okay, so this delta G up, okay, is a function of temperature. Okay. So if we assume, okay, we assume that this reaction right here, okay, is a first order reaction. First order reaction. Okay. Then the rate of this reaction, R, okay, is simply equal to Kf, the rate constant of the four reactions times the concentration of the oxidizing agents, okay? Okay? So which is equal to R forward is equal to Kf CO exponent minus delta G over 1. So because this four reaction, right, is a cathodic reaction, okay? Cathodic reaction is the four reaction because these produce these. Okay? So this is, we just write this as GC, okay? GC, okay? So this is the initial reactant. Okay. And C naught right here is the concentration of this oxidized species. Okay. So, suppose, okay, this is potential, okay? Suppose, okay, we can so for a chemical, okay, chemical reaction, okay, the delta G, okay, forward, okay, is fixed. Okay. The difference between an electrochemical is an chemical.
丢卡没有选择等于零那个，
对的，
哦，那是内头，
这个是吧？
左边的
左边那个内，
对的，
哦，下面那个内丢卡没有选，
delta reaction 给你。
哦，
不好意思，我尽量写好一点啊。我尽量写好，写的不错啊。
So for a chemical reaction, this delta GF is fixed, okay? The difference, for a electrochemical reaction, this is different, okay? So we can increase or decrease this Gibbs energy difference, okay? By changing VM, okay?
是哦，
啊？
是哦，
什么呢？是哦。
为什么？为什么可以哦？
对 we lower the PM, okay, we can decrease the delta PF. And this will lead to a decrease in activation energy. Okay, which would lead to an increase in reaction rate. Okay, so previously, okay, let's say, okay, initially, so this is V1, okay, and this is V2. So, okay. So this here, okay, corresponds to delta GC, okay, at V1. This is delta GC at V1. Okay, and this is delta G A at V1. Okay, so previously, okay, so we have this activation energy to overcome, okay, previously, okay, to reach the transition state, okay, and then once we're in the transition state, we can flip over. This reaction will become spontaneous to go from the transition state to the final release. Okay? But it has to overcome this activation energy barrier. Okay? So what if, okay, we're artificially lower the potential of the electrode, okay, so that we're now at V2. Okay? So this upper curve, right? Okay? This upper curve, okay, the upper curve is at a lower potential. Okay? And because of this, so that it's more negative, okay? It's more negative, okay? A more negative potential means that that it has a higher electron energy. Make sense? So this upper curve is at a lower potential, okay? Lower potential, okay? And so it's more negative, okay? And because it's more negative, it has higher electron energy, okay? So that it's easier to go over that hump. Okay? So the higher, okay? The higher, okay? The higher the electron energy, okay? The lower the activation energy. Okay? You see that? So, which one do you think is higher? in terms of V1 and V2? Which one has higher energy?
哪一个的那个电子？
对，V1 or V2 has the higher energy?
比较 V2 好。
V1 is higher.
啊，
V1 has a higher energy because is at a lower potential. Okay, V1, the upper curve, this is V1, okay? V1, okay? This is the upper curve, okay? It has a lower potential and therefore a higher energy. Okay?
它potential 很高吗？potential 不是 V2 比较小吗？
什么？
就是说 low potential 会有 higher。
A more negative potential. A more negative potential. Lower potential means it has lower potential to overcome to reach this transition state.
哦。
This potential, this and this is the same, okay? Potential, okay? This they're the same, okay? Okay. So it has okay. So at V1, okay, because the relative position of this is higher than this, right? So the electrons must stable here.
嗯
So a forward reaction is favored.
嗯
Make sense?
嗯
Whereas now you're at V2 because at V2 the energy is lower here.
嗯
So the reverse reaction is favored. Make sense? So for this reason, because the delta G, okay, C, okay, is less than the delta G A, right? This is bigger than this, right? The reaction moves right. Right? So the reaction moves down because this is lower electron energy. The small thermodynamic is stable. Okay? So as potential, okay, moves from V1 to V2, okay? There is a change, okay? So this change right here, okay, So, moving from V1 to V2, we lower the electrode's energy by this much, F delta V. Okay?
这个 F 是谁？
啊，
这个 F 是谁？
F 是那个什么 Faraday's constant。
为什么要乘上？
这是一个 energy 的，这是Coulomb per equivalent. Coulomb times voltage is energy. Okay. So as potentials move from V1 to V2, the change in energy, okay, is so in doing that, in moving from V1 to V2, okay, the relative positions, okay, of the starting place and the transition state change. Okay, so now we have a new transition state here, right? So previously, we need to move this much to reach the transition state, right? Now we need to move, this is the new transition state, okay? From here to here. Right? So the activation energy very increase. Right? Yeah? So previously we only need to move this much to reach the transition state. At the new, we now have a new transition state where we have to input a higher activation energy to reach that transition state. Make sense?
可以再一次吗？
Huh?
可以再讲一次吗？
Previously, we need to move delta GC, okay, to go from oxidized state to transition state. Now we're at V2, right? We have a new transition state. So now we need to input a much larger activation energy to go from V2 to the new transition state. In other words, the activation energy barrier is increased, right? So it's harder to reach that state. So that's going to have consequences to the direction of the reaction. It'll get reversed. The reverse direction is straight. Okay. So if we define, okay, define beta, okay, as fraction of F delta V, okay. That parts to the activation energy. Cathodic reaction. Okay. So we know that this is a change in energy, right? To go from V1 to V2, right? So due to this change in energy, which is F delta V, okay, now we have a new transition state, okay? So the consequence of this new transition state for the reduced state is that now the activation energy pair going from the reduced state to the new transition state is changed. Okay? And that change is the fraction of input fraction that record so the noted activation is changed by so if we define beta as a function, as a fraction of f delta b, okay, that imparts the activation for 5 activation energy change. Okay? So beta is the fraction of f delta b. That changes. Okay, that the 5 activation energy going this way. Okay, then 1 minus beta. Okay, this fraction right here. Okay. 1 minus beta delta b. Okay, is this here. Okay, so previously the activation energy, okay, going from the reduced state to the transition energy is delta GA V1, right? Now is delta GA V1 minus 1 minus B times F delta. Okay? Okay? So the change in activation energy. Okay? The change in activation energy going from V1 to V2, okay, is the difference between this, right, going from here to here, the change from here to here, right, in the forward direction, and the change from this to this minus this, right? And so for the cathodic reaction, cathodic reaction is forward, okay? So delta G C, right? Delta GC V1 or V2, okay? V2, right? V2, delta GC V2, okay? We're going to calculate this energy, okay? This change, the change in this energy, okay? Is equal to delta G C V1, okay? Plus F plus F delta V, right? And subtracting this. Okay? Minus 1 minus beta. Right? This and this minus that. Right? Which will give you this. Right? Okay, so which is equal to delta G C V1. And here is plus F delta V minus F delta V plus beta minus F delta V. Okay, so this cancels. So we have delta G C V1 plus beta F delta V. So, which is this and to that, which is equal to this. Okay? And so for another reactions, okay? Delta G A V V1, which is simply equal to this minus that, right? To get from here to here. Right? So this is equal to delta G V1 minus 1 minus beta delta V, okay? Which is equal to, okay, so that is that. And delta V, okay, is positive. Okay, it's positive because okay, this stands for because. Okay, V slash C stands for because V2 is greater than V1. Okay, so therefore, to derive the rate, okay, the changes in rate, okay, the changes in rate going from here to here, how changing the potential of the electrode from voltage 1 to voltage 2, how that reflect the rate, okay, changing V and V1 to V2. How that change the rate. Okay? So that change is reflected by RC of V2, which is equal to so this is the forward reaction, okay? this is KC. C naught. Exponent. Okay. Minus WG. Which is equal to C naught exponent. So this is equal to this. Okay, so it's minus delta GC V1 plus so which is equal to KC naught exponent minus delta G V1 plus beta F V2 minus V1. Okay. So So because the V2 and V1 is so V2 and V1 is arbitrary. Okay, arbitrary. Okay. We could set it so that they're relative to each other. Okay, they're relative to each other. Okay. Okay, this is V1. So we just need to define that they're relative to each other. Okay, so we can set V1 is equal to 0. Okay? We just arbitrarily define this point to be our reference point. Okay, so if this is the case, okay, and this, then delta GC, okay, V1, okay, this is good, okay, this is equal to a constant. This is equal to a constant. Okay. And so KC now C now exponent minus delta G C. This is 0, I think. We've already. Okay. This is equal to a constant. Okay. We set that to be equal to KC. said V1 equal to 0, right? This V1 is equal to 0. If this is 0, then this is a constant, this is a constant, this whole thing's a constant. So we set this constant Kc. Okay. And then since there's only V2 left, okay? V2, this is our reference point, V1, we'll set that to 0. There's only V2 left, okay? So we just drop the 2. V2 is down to V. Okay, we're measuring V2 relative to V1, right? V1 is 0, so we just set V. We can just drop the constant 2, okay? So if that's the case, RC, okay? This equation right here, down here, okay? RC V2 is now equal to RC V, right? We're gonna drop this. We're gonna drop this 2. Okay. This is equal to Kc naught C naught exponent. This D1 right here is equal to 0, right? So this first term right here is a constant, right? That constant is equal to Kc. Yeah. So this is Kc. Okay? So this term right here. Okay, this term right here is Kc. Okay? So Kc times C naught. Okay? Again, Kc times C naught times the exponent times this term right here. Right? So V1 is 0, so there's only V at V left, right? So is simply minus V at V over RG. So this is our rate equation. Okay? Going from V1 to V2, okay? The rate constants change to this. Okay? Which is a function of beta. Okay? Beta, this is delta V. Okay? This changed to here. Okay? So so now we want to use this. We want to use this rate equation and find use rate equation. Okay. Define as a function of potential. Okay. We have a rate equation, right? These rate equations tell us for whatever change in voltage, we're going to get a change in rate, right? Yeah. So how is that voltage related to the current? Is what we're going to now find. Okay. So okay, so for cathodic reactions, okay, so for cathodic reactions, the current, okay, current, okay, this is negative, okay, by convention, okay. So if this is the case, then C, okay, over that, okay, this is equal to rate, okay, because this reaction right here, okay, this is a O plus E okay, this is a single electron reaction, right? So for every single mole of, for every single mole of oxygen, I mean oxidized species that get reduced, there's going to be a mole of electron that's used up. Okay? So that mole of electron is pi to, if you divide that by if you multiply that rate, okay, that Kc right here, right, is Kf, okay, Kf or Kc, okay, cathodic direction, forward direction, right. That Kc, right, is a function of this, right, CO, Kc. Kc is a function of the CO. This is a function of the composition, okay? And what is it that I say? It's a function of this rate is a function of delta GI. Sorry about that. So this Kc is equal to that, right? It's a function of the delta G, right? So that rate, okay, we can get, if you multiply this rate expression with that, okay, we'll have the equation for current. Okay? Yeah, you see that? If we derive the equation for the rate, right? The rate is equal to this, right? Okay, this is for the cathodic direction. Right? If we multiply this rate expression with that, we have current. Okay? Yeah. So this rate, okay, which is equal to minus RC, which is a function of the voltage, right? This rate is a function of the voltage, right? Yeah? Yeah? So this rate expression is a function of voltage, which is equal to minus Kc, C naught exponent, minus beta Fe over RT. Okay? That's what we derive here. Okay? And so similarly, okay, for the reaction in the reverse direction, okay, we can get another expression for I over A, which is defined in another direction. Okay. This is RA. A stands for another. Right? This is also a function of voltage. This is Ka. There is no negative sign now, okay, because this is another direction. Ka, Cr. Okay, R stands for the reduced species. Okay, concentration of the reduced species times the exponent, and 1 minus beta Fe over RT. Right? so now remember at equilibrium condition, okay, at equilibrium, right? We have the potential is equal to U, right? When I equal to 0, when there's no current, right? So at equilibrium, right? At equilibrium, IA over F is equal to IF, IC over F, okay? This is the absolute, right? Because the forward reaction and the backward reactions is the same, right? Okay, so this is the same, right? And this is equal to I naught over F. This is the exchange current density, okay? I naught is the exchange current density. So for a metal, okay, as a function of metal, okay, is the current density at equilibrium, right? So at equilibrium, okay, at equilibrium, we have, so we this is equal to this, right? These two are equal, right? The forward reaction and the backward reactions are the same. So I naught F is equal to KA CR epsilon 1 minus beta U over RT. Okay, this is the reaction rate in the Nordic reaction, right? This, okay? And this V is substituted with U, right? Because it's at equilibrium. Yeah? Understand? And this is equal to, this is in the anodic direction. This rate is equal to the rate in the cathodic direction, which is Kc plus C naught exponent minus beta Fu over RT. Okay? This is the same. Forward and backward, the rate is the same, right? And again, like the V here is replaced by U, okay? Because this is at equilibrium, okay? So using this reaction, okay, rate, okay, in the anodic direction, okay, taking this over, so IA, okay, so IA over F, okay, which is equal to this, okay, so it's KA CR 1 minus beta, okay, over RT, okay. If we multiply this expression at equilibrium condition, okay, which is Ka CR 1 minus beta at U over Ka CR 1 minus beta at U. Okay, this is 1, right? This top and bottom are the same, so this is 1, right? 1 constant, and this is so, right? And here, the V is changed to U, okay, to reflect that as the is at equilibrium, okay? So if we multiply this with that, which is 1, okay, then we can do some canceling, okay? So Ka cancel out with this, CR cancel out with this, okay? And so it's 1 minus B, 1 minus beta, okay? And F times V, and F times U, okay? So, this is 1 minus beta F times V minus U, right, on top, yeah? Right? Over, 1 minus beta, oh, this is gonna cancel, right? We'll just keep it, okay. RT, and F to U, okay, is equal to IA over F. This cancels, this cancels. You get, hold on a second. This not the exponent. There's an exponent. Okay. So there's an exponent here. There's an exponent here. There's an exponent here. Okay. So, let me start over. So, okay, so I over F, and that is K, So exponent of this over there, okay? So, and so this is equal to, everything inside is time. this is going to simplify out to this. I naught exponent 1 minus beta at v minus u over r. I is going to simplify that. Okay? So this gives the current, another current in terms of the exchange current. This is the current at equilibrium. Okay? And this is the equilibrium potential U. Okay? So this is the current is now a function of the potential, the temperature, and the beta, okay? And the exchange current density. Okay? So another form of this, okay? This simplify out to IC is equal to negative I naught exponent minus beta v minus u over. So we define this term right here. Okay? So we define v minus u as define this as the surface potential. Okay? So this is the driving force. Okay? This is the driving force. Okay? So this surface potential is equal to V minus U, okay? Which is relative to the same reference vector. So which is equal to this V right here is equal to Pm minus P solution. Okay? This is the equilibrium potential. This is the potential of the electrode. This is potential of the solution. Okay? So for the net current density, I. Okay? The net current density, I is equal to IA plus IC. Okay? I is equal to IA plus IC. Okay, this is the net current density. Okay? This is equal to I naught. We have expression for the IC, meaning the anodic current density. We can derive the same for the cathodic current density. Okay? So we have IA and IIC. Okay? They're IA and IC. They're both a function of the exchange current density, which is I naught, okay, times the exponent 1 minus beta. That the surface potential times R minus exponent minus beta. That surface potential over. Okay? So we derive the expression for the anodic current density. Okay? So this is the anodic current density. Okay? The cathodic current density is simply that. Okay? add these two together, we get the net current density. Okay? And this expression, okay, for the net current density, which is a function of the surface potential. This expression right here, okay? This is called the Butler-Ulmer equation. This is the Butler-Ulmer equation. For elementary reaction involving transfer of a single electron. Okay? And then so in simplified term, okay, the Butler-Ulmer equation, okay, simplifies to I equals to I naught times the exponent alpha A F over RT minus alpha and exponent alpha cathodic F over RT. Okay, so this right here is the anodic transfer coefficient. And this right here is the cathodic transfer coefficient. Okay? And this alpha is simply 1 minus beta. Okay? And alpha c is equal to minus beta. Okay? And alpha A plus alpha C, this is equal to n. Okay? Which is the number of electrons. Okay? So for elementary reaction involving a transfer of a single electron, that n is equal to 1. And this Butler-Ulmer equation can be extended to electrons transfer more than 1, higher than 1. Okay? And this expression right here, F surface, F surface and RT. Okay? This is unitless. Okay? If you multiply all this out, this is unitless. Okay, because they need to fit within this exponent. Okay, so this is unitless. So the Butler-Ulmer equation, okay, is a function of the exchange current density, which is current at equilibrium. Right? And alpha A, alpha C, okay, which is the anodic transfer coefficient and the cathodic current transfer coefficient. And So now we have an equation. We have an I, which can measure that with the potential stat, right? We have this, the surface potential. Okay, the surface, the surface over potential. This is the surface over potential, which is V minus U, which is potential of the metal minus potential of the solution minus the equilibrium potential. Okay? Yeah? This is the sum of these three. Okay? Right here. Okay? You have the temperature that we can measure. Okay? And so, for a reaction, for an electrochemical reaction, okay, we can have an I right here, right? We can measure the I, okay, and then we can fit the data of the voltage, the I versus the surface over potential, whatever that relationship is, we can fit it to this curve to get the transfer coefficient for the Nully transfer coefficient and the cathodic transfer coefficient. Make sense? So now we have a relationship that can describe kinetic behavior for this setup. For a set current, I, we measure the voltage, and then we can get the monodic and cathodic transfer coefficient to describe the system. Okay? You good? 你要说什么？你要说什么吗？
那个麦克，
什么？
那个麦克，
你听不懂吧？就是你现在有一个 system 是这个对吧？这是你的 two electrode system，对吧？这个 anode and cathode，对吧？这个 anode and cathode 它有一个，它就是 O plus E 就是 R， 对吧？这个 anode 还有这个 cathode， 它给了一个 electron 之后，对吧？它就跑过去了，get reduced over here， 对吧？然后它的 reaction rate 是跟这个 current 有关，你可以 measure 这个 current， 这个 I， 你有这个 temperature， 然后你 measure 这个 current 的时候，你看它的 potential 是什么？你可以，然后你就把它的那个 potential， 还有它 current 放在这里面，你就可以找出它的 alpha A 还有 alpha C。这 alpha A 跟 alpha C 是 characteristic for 这个 system。
哦，所以找出来可以做什么？
你就知道这东西在哪一个 current 的条件下，它会给你多少 volt， 然后那个多少 volt 就跟你讲这它知道这边的东西是有多厚，多少 mass。
哦，好，
知道吧？因为这个 rate 对吧？这个 rate 是跟它的厚度就是 mass 有关的，好吧？OK。